Alright, today the objective is to prove that our tree method is complete. So we want to prove the completeness theorem. That is, if sigma syntactically entails A, then sigma... Wait, I think I messed that up. If sigma semantically entails A, then sigma syntactically entails A. We want to show that this is true for our tree method, because then we know that the tree is at the very least complete. The next video will show that it is also sound. Therefore, if it's complete and sound, we have a good argument. Now, the completeness theorem, we do not have all the tools that we need to prove it yet. So we need to prove a lemma, as you can see. Lemmas are things that you prove before a theorem that help prove the theorem a lot easier. So what is our completeness lemma? What are we going to prove? Well, the completeness lemma says, let B, capital B, be an open branch for the tree sigma not A. Now we're going to let V be the interpretation induced by B. Then for all sentences, V of P equals 1 if P is on B, and V of P equals 0 if not P is on B. So what we're going to do is prove that very last statement. For all sentences, that will be true. Now, how are we going to do this? We are going to do a proof by induction. Now, if you've never done proofs before, you probably haven't heard of that before, and that's okay. We're going to walk through this, hopefully, nice and easy. And if it still doesn't make sense, I have another video explaining it in more mathematical terms. So, what is a proof by induction? Basically, what we do for a proof by induction is we're going to show that this lemma is true for some very small, simple case. And then after we show that it's true for that small, simple case, we just assume it's true for some more things. This is going to sound very abstract. It'll make more sense in practice. After we show that it does hold true for something, we'll assume that it's true for some more stuff. And then by that assumption, which will be referenced as the inductive step, by that assumption, we can then show what we want to show, and that is that this lemma is true for all sentences. Now, for all sentences, that includes basic parameters, conjunctions, disjunctions, conditionals, biconditionals, and negations. Now, a full proof would do a proof by induction for every single one of those cases. We are just going to do the conjunction case, and if you feel so inclined to do all the others, you may. It's just that if you're taking a class, I highly doubt you'll be expected to write out an entire full proof on a timed test, because that's going to take a lot of time. Even if you have it completely memorized, it will take time to write it all out. So we're going to show that the completeness lemma is true for conjunctions. So let's start with our proof. Let's go back to white, shall we? Let's say proof. So like I said, we want to show this is true for some small case. This will be called the base case. So our base case will be when our sentence is just a single parameter. Nothing else, right? There's no conjunctions, there's no disjunctions. We just have a parameter P, right? And this will just be true by definition. This is true by the definition of evaluation. I think we defined valuation loosely in the last video, where we said the valuation of a parameter P is 1 if P is on B, and it's 0 if not P is on B. So our base case, when we're looking at a parameter, it's just true by definition. Now, here is our inductive step. Let's scroll down a little bit. Let's make some room. Here is our inductive step. Inductive step. Assume the lemma is true. So like I said, we assume the lemma is true for some more stuff, and then we use that to prove that it's true for everything. Assume the lemma is true for phi and psi. These are Greek letters. Now what does that mean? So that is, if phi is on B, then V of phi is equal to 1. If not phi is on B, then V of phi equals 0. Likewise, if psi is on B, sorry, this is probably not very entertaining, but I just want to explain this because it's important to know. Then V of psi, let's not write phi again, then V of psi is equal to 1. And if not psi is on B, then V of psi will be equal to 0. So that's our inductive step. We are assuming that. Now what we want to do is show if phi and psi, oh my gosh, I cannot write, if phi and psi is on B, we want to show that the valuation of it will be 1. And then we want to show that if not phi and psi is on B, the valuation of it will be 0. So if phi and psi is on B, since B is a complete open branch, it must be the case that phi is on B and psi is on B. Now, by the inductive step, since phi and psi are both individually on B, by the inductive step, what can we conclude? We can conclude that the valuation of phi is equal to 1, and the valuation of psi is also equal to 1. Then it immediately follows that V of phi and psi is equal to 1. So that was pretty easy, I think. And now we're going to show that if not phi and psi is on B, then the valuation of phi and psi will be 0. So if not phi and psi is on B, what can we conclude? What follows from that? If not phi and psi is on B, it must be the case that not phi or not psi is on B. One of the two or both are on B. Since in either case, right? In either case, V of phi will equal to 0, or V of psi will equal to 0, or both V of phi and V of psi equals 0, or V of phi and V of psi equals 0, right? Because it's the case if not phi or psi is on B, then it's the case that one of them or both of their negations are on B. Then again, right? So that means at least one of them is false. Then it follows that the valuation of the valuation of phi and psi will equal 0, right? That's again because one is going to be false, so that means the valuation of the conjunction will be false. This is just like the same as when we were using t's and f's. Now we're just using 1s and 0s. So that would be the end of the proof for our lemma, just for this case. And we're only going to do one case. I'm not going to do disjunction. We could, but you could do it yourself. It would follow. If you understand this, you'll understand how to do the rest by yourself. So now we have the lemma, and you're going to see how that comes and helps us prove our theorem. Now remember, our theorem is if sigma semantically entails A, then sigma syntactically entails A. So to prove the completeness theorem, we're actually going to do a proof by contrapositive, which means instead, we're going to show that if sigma does not syntactically entail A, it semantically entails A. So let me just write this out. Sigma does not syntactically entail A implies sigma does not semantically entail A. And this is logically equivalent to showing that sigma semantically entailing A implies that sigma syntactically entails A. They're logically equivalent, so I could prove one or the other, and both proofs will be a proof of the completeness theorem. It's just that the contrapositive is a lot easier to do. So let's do it. So, what to show? Let's write what to show. Our what to show. What to show. We want to show... Yeah, sorry, I'm scrolling a lot. So what to show? We want to show that if sigma does not syntactically entail A, that implies that sigma does not semantically entail A, and that will prove the completeness theorem. That will show that our tree arguments are complete arguments. Okay, so the first thing to do is assume that sigma does not syntactically entail A. So proof. Assume sigma does not syntactically entail A. Now, what does this mean? Last video, we said that sigma syntactically entails A if and only if the tree for sigma not A closes. So, if it does not syntactically entail A, then sigma not A does not close. So then, it must be the case that sigma not A does not close. And further, and there is an open branch, right? That's what it means if it doesn't close. If it doesn't close, there's an open branch. Call it B. So there we go. Now what else can we conclude? How can we get further to what we want? Well, we're going to let V be the interpretation. Let V be the interpretation. Let's spell the word right. Interpretation induced by B. Induced by B. Okay, now we're going to use our completeness lemma. So, by the completeness lemma, for all sentences P, V of P equals 1, if P is on B, and V of P equals 0, if not P, is on B. So this is why we needed to prove the completeness lemma, because we need to draw it in right here. We know by the completeness lemma, for all sentences P, V of P equals 1 if P is on B, and V of P equals 0 if not P is on B. Now, on our open branch B, right, the sentences, our premises sigma, they're on B, which means the valuation of those premises will equal 1, meaning they're true. And remember, not A is on this branch B, meaning the valuation of A is 0. Now, if you recall from last video, we said that sigma semantically entails A if and only if there is no valuation V such that V of sigma equals 1 and V of A equals 1. However, we're about to show that such a valuation exists, which means that sigma does not semantically entail A. So, since sigma appears on B, and since not A appears on B, we can say that the valuation of sigma is equal to 1, and the valuation of A is equal to 0. Now, as I just said, sigma semantically entails A if and only if there is no valuation V such that V of sigma equals 1 and V of A equals 1. This is what we discussed last video. Now, I just found such an interpretation. Thus, we can conclude that sigma does not semantically entail A. Sigma does not semantically entail A as desired. And that is a proof of the completeness theorem for our tree method. So if you don't even know what we just did was show that our tree method is complete. Next time, we'll show that the tree method is sound. And since it's sound and complete, it's a good argument and works every single time. If you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.